Good morning, class. So you found it. You made it. Well, most of you have made it. I suspect there'll be some more people joining us soon. So, welcome to Friday of this is our second week of class already. So, our goal today is I'm going to work through a notebook it's a lesson that's posted on my GitHub repository. So I have a link here. There you go. So everything that we're going to talk about today is contained in a lesson that's posted on my GitHub repository here as a Jupyter Notebook file. You can go to this repository and then go down a few levels into the lessons folder, and this is Unit 1, Exploring Data, in that lessons folder. Okay, so my suggestion is you follow along with your eyes and ears, and don't be scrambling to take notes as I'm working through this, because it is all there for you. There's already a review posted for you, a summary of this lesson. Okay, so if you've done this before, you can't talk to me, but you can interact with me via the comment stream. I got the comments here on the computer next to me, and I'll take a look at them every once in a while. And so if you have any questions, just post them up there. All right, one more thing. I've been setting up 461 for some of you, just a couple of you. And so check your inbox, check your email with instructions to go and register for 1 credit of my section of ENVS 461, that's section 2, before the end of the day. Today's the last day of extended ad. All right. So say goodbye to this link. Boom. Okay. So I'm going to go over to, I have Jupyter Notebook open in a browser window here. And I'm working on a Windows computer right now. So but you know, Jupyter Notebook runs inside of a web browser, and it is mostly the same regardless of the platform you're running it on. All right, so I'm going to start a new notebook, a Python 3 notebook, and I'm going to call this notebook Exploring Data. Okay, and the data and mathematical models that explain or predict data, these are foundations of science, and knowing how to work with data and manipulate it is fundamental to doing science. So in this notebook, I want to do a bunch of things. I'm going to pull in a data set that is publicly available on the internet, on Kaggle.com. Kaggle.com is a data science website. It's fun. It's got a lot of data science competitions that people can join in, and dealing with data with wine, from Wine Enthusiast magazine. And we're going to take a look at this data. It has lots of dimensions, so remember, when I say dimensions, I mean columns in the data set, and it's got lots of examples. Those would be the rows in the data set, but the dimensions are different kinds of data, what we call data scales. Okay, so we're going to look at this, and then we'll make some plots of this data: bar chart, histogram, box and whisker plot. And then if we have time today, we're going to talk about what a normal distribution is, and we'll look at some examples. Okay. So the first thing I'm going to do here is I'm going to import some packages, and so Python uses packages to simplify data analysis and data manipulation. And so I'm going to import NumPy or NumPy as NP as a shortcut. I'm going to import pandas as PD, and then I'm going to import, I think this will only import 3 packages today. matplotlib.pyplot as PLT. Okay, so you guys have seen that before. All right, and now I'm going to import this data set from this Wine Enthusiast magazine. And this data set is posted on my GitHub repository. So one thing you can do, we've done this in class where we import data from a local file, but you can also import data from a web address. So let's see if this works. Got too many quotes. There we go. So this is a URL to my GitHub repository, and so this data set's called Wine Mag Data 150K, 130K. So there's 130,000 examples in this data set. It's a very big data set, and it's a zipped up file archive. Okay, you'll see this sort of thing again as we work through the class. And so now I'm just going to import this data as a data frame using the read CSV command, and instead of typing the file name, I'm just going to reference this URL, this web address, and then I just got to do one more thing in this particular case. Because the data is zipped up, it's archived, I've got to specify the compression protocol so it can read this correctly. So this is a big data set. This might take a minute to import. No, it took no time at all. So let's take a look at the data set. Oh, it's not wind data, it's wine data. Okay, so what we see is this data set has, well, there's a bunch of dimensions. So that, in row 1, column 1 is just an index, and then you have country, so where the wine is from, description, designation, the number of points that Wine Enthusiast awarded this wine, price, so you can see sometimes the price isn't given, it's listed as not a number, the province, regions, and taster name, who tasted the wine, taster handle, Twitter handle, title of the wine, variety, and winery. So there's a lot of different dimensions to this data here. And why don't we just look at the first couple rows of this data set right here. Okay, so you can already see that the data that's in these different columns, the different dimensions of data here, are all over the place. Some of the data is numerical, some of it is not. Some of the data is missing, and that's a potential difficulty. Some of the data is like province. In the United States, that means state, but in other countries, it means something different. Okay. So I'm going to paste in here into this cell. I'll make it a markdown cell. And I'm going to paste in here some definitions. And what these definitions relate to are 4 different types of what are referred to as data scales that you'll encounter in your data. I think it would be fair to call these data types, different types of data. But these 4 data scales, 3 of them are usually numerical. 2 of them are definitely numerical. One of them could be numerical or not, and then the 4th one is tends to be sort of categorical. Okay, so let me paste these definitions in here for you. And I just got to separate them. Okay. And I think that maybe so nominal data. These are categorical labels. They could also be symbols or names. And none of these category names have numerical significance, and there isn't a natural order to this data, this type of data either. So, let's think of some examples of what nominal data would be. It would be things like, in this data set, the wine variety, the winery name. These are nominal dimensions of this data set. There may be a finite number of different labels that you can have in a nominal dimension of your data. Think of like, if you're maybe doing a tree assay and you're saying, you're out there looking at trees to see if they're infested with gypsy moth, and you end up saying just yes or no. So for tree 1, is it infested? Yes or no. Tree 2, is it infested? Yes or no. That's nominal data. Okay, so some of you are going to have data that's like this. All right. Ordinal data. Let's make that strong. So these are numbers, labels, or symbols. So this is the gamut. It could be numbers, labels, or symbols. But the thing is that's different about ordinal data is it has a natural order. It has a hierarchy associated with it. And here it says there's no guarantee that the intervals between adjacent labels are uniform. And I can give you an example of that. So the list of finishers in a race, runners in a marathon. It could be that you have a list of finishers, 1st, 2nd, 3rd, 4th, 5th, 6th place. There's an order to the finishers, but you don't know the relative amount of time that it took the different runners to finish. So for example, the difference between 1st and 2nd could be like 100 milliseconds, and the difference between 2nd and 3rd could be 2 minutes. So you can have different intervals between the values, but there is a definite order. Okay, so so this type of data can be numerical, but it's you gotta be careful because it doesn't. If you list your data 1, 2, 3, 4, 5, it's not telling you that those data points are equally partitioned on the number line the way the numbers 1, 2, 3, 4, 5 would be. Okay. So some of you might have an example of data that to take my previous example of the gypsy moth infestation. So instead of just saying yes or no, the tree is infested, maybe you give it a rating. So you have no infestation, some, or complete infestation or something like that. So those are 3 different levels of infestation that definitely have an order and severity. Okay, so that would be an example of ordinal data. All right. Next up, interval data. Interval data are numbers and they have a definite order like ordinal data, but there's a well-defined interval between the values. And so an example of this in our data set here would be the year of the wine was produced, the vintage. So 2018 is the 2019 as 2019 is the 2020. So they have the same spacing between adjacent values on this number scale. That's what makes it interval. So there's a little, and the last type here is called ratio data. And the thing that is different between ratio and interval data is that ratio data has a well-defined 0 point. So if you're taking measurements with, the types of measurements that you would take with scientific instruments, graduated cylinders, meter sticks, stopwatches, those types of data tend to be ratio because they represent measurements that have a 0 point on a scale. An example of a scientific measurement that isn't ratio would be, well, I should be careful. I was going to say temperature, and the reason is because 0 Fahrenheit and 0 Celsius mean different things, so there's not a well-defined 0 point when it comes to temperature scale, but there is an absolute 0 at 0 Kelvin. So it just depends, I guess, on the units that you're using. An example of data that is interval but not ratio would be something like year, because there is no 0 year, if there is in our calendar, but years go beyond that. So, if you think about, a meter stick, you're measuring the lengths of pea plants that are growing in your greenhouse. You're not going to actually measure a length of 0 in practice. But what I'm getting at is that the instrument that you're using, the scale that you're using, has a 0 point, and there's no such thing as a negative value. Like, you're not going to measure the length of a pea plant and say it's negative 10 centimeters. All right. So you need to have a grasp of the type of data that you have in order to know what kind of analysis you're going to do. Okay. So you need to know whether you are working with nominal, ordinal, interval, or ratio data. All right. So let's work on visualizing some categorical data. So what we're going to do here is we're going to visualize the sum of the varieties of wine in the data set. Okay, and the way we're going to do this is we're going to make a bar chart. Okay, and so what I'm going to do in this cell, and again this is posted up on GitHub, is a prototype that you can reuse to make your own bar charts. And there's stuff that I have to do in the front because there's actually a ton of different varieties in this data set. So I don't want to plot them all, it would just be overwhelming. So I'm going to collect the wine varieties into a subset of wine varieties using a tool called collections. So I'm going to import this collection tool. And I'm going to then count up the number of varieties using this collection tool, a tool inside this collections package called counter. So I'm going to go to my data frame is called wine data up here, called wine data. So this is all my data, and I'm going to extract from that wine data the column called variety. Okay, so that's this column right here. So it's things like white blend, Portuguese red, Pinot Gris, Riesling, Pinot Noir. Okay, and it's a little bit of a huge data set. Some of the values aren't well defined, so I got to do this in order to correct for that. You won't end up doing this probably with your data. And then I'm going to convert this into what's referred to as a dictionary. And all I want is the most, in this case I only want the most common varieties. I'm going to pull the most common varieties out. Okay, just the 7 most common varieties. Okay, so I'm going to run this, and it helps if I have no spelling errors. Okay, and let me just show you the results here. Okay, so what I've done here is analogous to what you would do in a spreadsheet. You could do this in a spreadsheet by making a pivot table. And so what it's done is it's gone through this collections.counter tool has gone through all the varieties in my wine and counted up how many of each variety there are. And then what we're doing here is only looking at the most common, the 7 most common varieties in the data set. So Pinot Noir is the most common, and there were 13,272 examples of Pinot Noir in that data set. Chardonnay, there was 11,752. Okay, so there's more varieties than what are shown here. I'm just looking at the 7 most frequent varieties. Okay, so the thing, so what I'm dealing with here, variety is it's a nominal dimension to my data, and when you work with nominal data, usually what you're going to do is tabulate the frequency of different values, which is exactly what we did here. We tabulated the frequency of this, well, restricted to the 7 most common varieties of wine. Okay, so in the process of exploring your data and then presenting your data, one of the things that you're going to want to do is do some sort of description of your data. And descriptions can be numerical, and next week we'll get to the point where we're talking about descriptive statistics, and that will be measures of central tendency like mean, median, and mode, standard deviation. But descriptions can also be visual. Okay, so just think on that a second. When I say describe your data, maybe a better word in this context might be summarize your data. You could summarize it using statistics, but you could also summarize it visually. Okay, and in this case, when you're dealing with frequencies of different counts of different nominal values in a data set, that what you're going to make, if you want to do a visual presentation of those frequencies, is a bar chart. Okay, so that's what we're driving at here. All right, so what I'm going to do is, this type of data structure here is called a dictionary in Python, and it's got keys, all right, and it's got values. So each key has a value associated with it. So, we want to look at these things separately. So what I'll do is I'll create, the keys are the varieties. So I'm going to pull the keys out of the dictionary, and the counts are the values. Okay, so I'll pull those out, and now I'll use matplotlib, referenced by PLT. It's got a tool called bar for bar chart, and what you pass this function in order to use it is the thing you want to be along the horizontal axis, varieties, and the thing you want to be on the vertical axis. Okay, so there it is. Got a bar chart, and it is a mess down here because the variety labels are words and there's not enough space. So there's a bunch of ways you can handle this and make it look better. Let's do this here. let's take the X ticks labels and rotate them 90 degrees. And at the same time, let's add a Y label here. The Y-axis represents the frequency of these different kinds of wine. There we go. And in this case, the frequencies are ordered from greatest to smallest, but it wouldn't necessarily have to be the case. You know, one thing to realize about a bar chart is there's no logical, well, I shouldn't say logical, there might be a logical order. There's no natural order to the values that you're plotting along the horizontal axis. It's not like, you know, this isn't a number line. Pinot Noir is not less than Chardonnay, is not less than Cabernet. This is just an order. You could use a different order to present the data here. Okay, but you know, when you look at the data visually like this, you get, you know, very quickly you get a understanding of the relative frequency of these different varieties of wine in this data set, and quicker than you would just looking at a table of numbers like up here. All right, so this is a great way to summarize nominal data with a bar chart. Okay, well, what about summarizing? What about summarizing numerical data? How should we? And so the difference is with numerical data, so this could be most likely ratio or interval type data. You have a situation where there is a natural order to the data, and if it's interval, there's uniform intervals between the data. And the answer is, the way to summarize it visually is with a, well, one answer is a histogram. Okay. All right, so now let's prototype how you would do a histogram. Let's take a look at I am okay, let me copy and paste. Let's take a look at some of the data here. Oops. So let's pull out the scores data. So let's call it scores. Maybe I should call it points. But let's pull out this column of our data set, the points data, and let's take a look at it. All right. So it looks like it actually looks like it's arranged in order of smallest to the largest, and it looks like 87 is the smallest value you can have. Let's see, how many wines are scores? How many scores are there? So I can find the length of this data set. Yeah, so there's just shy of 130,000 wines in this data set. And maybe we want to know, you know, well, what are all the unique values that are in here? You can use, there's a function in NumPy called unique that will look through all this data and it will show you all the unique values. So it looks like I was wrong. There's wines that are scored 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 99. There's even 100 somewhere in here. And then there's a bunch of wines that aren't scored. So they're rated not a number. Okay. So we don't want the scores that are not a number. We got to kind of peel them out of here. So the way we can do that is we can say, you know, we want the scores where the scores are greater than 0. And by the way, doing this sort of thing is what I'm here to help you with. You know, if you're like, how do I get rid of the knotted numbers in my data set? Ask me if you can't figure it out. This is one way. So basically, what's going on here is I'm looking for all the scores that are greater than 0, which would exclude the knotted numbers, and then I'm just pulling those scores out of the data set and saving that reduced data set as the variable scores. I'm like overwriting that data set. So now if we did got rid of those knotted numbers, they're not there anymore. All right, so from this point, making a histogram is pretty easy. You use the hist function, which is part of matplotlib, and the histogram is going to be histograms of the score data, and then you can specify how many bins you want. Let's just pick a number 10. You can specify the color you want your bins to be, maybe green, and let's take a look at it. Okay, so maybe we want more bins. Let's do 20 bins. Let's do, how many different values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 17, 18, 19, 20. There's 21 different values. Let's do that. Okay, so now I have a bar in my histogram for each of the possible values, and the height represents the frequency again of that particular variety of, or that score in the data set. So the horizontal axis is point score and the vertical axis is frequency. So this looks like, maybe this is 90, and for whatever reason there's not a lot of, it looks pretty normally distributed, except for this score right here. For some reason there's less scores. I don't know, maybe that's 89. So you can make a histogram, and this is a summary of your data, because at one glance you're seeing the distribution of your data. You're seeing the relative frequency of different scores. I guess we should pause and think about what kind of data this actually is. What's the data scale for scores? And here we're treating it as interval data, but we gotta be careful. It's not really interval data, and the reason is because these scores aren't assigned by an instrument that's taking a measurement of the wines. These scores are assigned by people, so there's a subjectivity baked in here. And in other words, there's no guarantee that the relative difference between let's say an 89 and a 90 score is the same as the difference between a 90 and a 91. A 91 might be a lot better than a 90 compared to a 90, or in comparison to a 90 compared to an 89. The relative intervals aren't the same. But let's treat it as interval data here, and keep going. So histograms are great ways of visualizing complete data sets. We're looking at all the data here. Every single score in this 130,000 example wine data set is represented on this histogram. Every single score is here. Another way you can summarize data sets like this is, so again, numerically, and we're going to talk about that next week, means, medians, modes, standard deviations. But I really like visual summaries of data sets. I just learn more by looking at a graph than I would looking at a table of numbers. All right, the two complement each other. So if I had this figure in my paper, I could write a caption that lists what the mean and the standard deviation is underneath it, for example. Okay, well, let's keep going. So another way that you can summarize data when it's interval or ratio is, instead of a histogram, do what's called a box plot. or a box and whisker plot. Okay. And so this amounts to just, instead of using the hist command function to generate a histogram, use the box plot command. And we're still plotting the scores, and the X label's the same. Let's take a look. Okay, so the box plot is it's turned on its side here, and now the point scores are on the vertical axis, and there's only a single there's only a single box plot here. It's labeled 1. You could turn that off. Actually, what we should do is, I got it wrong. This is the Y label is the point score. So what you're seeing here is these lines represent different statistics, summary statistics of this data set. This is the median. The orange line here represents the median. Hold on a second. Sorry. The orange line here represents the median of the data. The width of the box represents what's referred to as the interquartile range. So if you divide the data up into 4 equal groups, 25% of the data is less than this line, 50% of the data is less than this line, 75% of the data is less than this line. So the interquartile range is the middle 50% of the data. Okay. These other lines represent the maximum extent, the maximum values. But here there's actually 2 values that are considered, or at least 2, that are considered outliers because they're beyond 1.5 times the interquartile range. That's what's going on here. So you can turn the outliers off. You could also, if you want to make this horizontal, you can do this. Just say, you want it to be vertical, false. You don't want it to be vertical. You want it to be horizontal instead. You can make it horizontal. So this is like the same orientation as our histogram up here. And here's a measure of the middle of your data. 50% of it is to the left and 50% of it is to the right. Here's a summary of where half of your data lies in this box between like 86 and 91 scores. And then these represent the maximum extent of your data, or 1.5 times the interquartile range, whatever's less. And in this case, there are a few outliers which are shown separately. Okay. So if you want to summarize numerical data, 2 good options are histograms or box and whisker plots. What you do just depends on the nature of your data, how many data sets you want to compare to one another visually. Okay. So let's do one more thing. This score data is, you look at this, and this looks like, at first glance, it looks like a normal distribution. It looks pretty, or Gaussian distribution. Bell-shaped curve. It looks like it's pretty symmetric about some middle point. Not perfectly symmetric, but it looks close. All right, let me show you what an actual normal distribution looks like. All right. And it just turns out that a lot of the statistics that we're going to do are based on the assumption of normality. Okay, the data is being normally distributed. So maybe the wine score data here is, maybe it's not. But what I'm going to do here, this little snippet of code here generates randomly distributed or normally distributed random numbers that have a mean of 0 and a standard deviation of 1. And I'm going to generate 10,000 of those numbers. And I'm just going to make a histogram of that data. Okay, so this is not real data, this is just generated. If I run it again, I get a slightly different histogram. You know, if I make the number of examples smaller, it becomes more noisy. But the more examples I have, the more smooth this normal distribution is. So now if you look at this distribution versus this histogram, they don't look that similar anymore. This one looks more broad, like it has fatter tails, and the central peak is wider. This has much longer but narrower tails, and the central peak seems to be more tight. Okay. And the you might have heard people talk about use this term parametric versus non-parametric, and you'll definitely hear it this semester. So when you're doing statistics this semester, some tests are for it'll say, you know, use this test for parametric data, or this is a test that can be used on non-parametric data. And you say, well, what does that mean, parametric? Well, just break the word down. Parametric means that you have something that can be parameterized. You can specify parameters for your distribution, or your distribution it can be completely specified using a relatively small number of parameters. And so the normal distribution is like this. The only two things you need to know the shape of a normal distribution is what its mean is and what its standard deviation is, or variance. You know, variance is just standard deviation squared. So in order to parameterize a data set that is using a normal distribution, there's two parameters, mean and standard deviation. But the reason this is weird is, you know, all distributions are parameterized. You know, they just mean different things. Like an exponential distribution also has a mean, and you can also calculate a standard deviation. It's, in fact, an exponential distribution is completely parameterized by one thing. It's mean. Okay, but I just want to say that when people in statistics say parametric or non-parametric, they're really mean normal or non-normal data sets. Okay. So let's look at another data set. I'm going to copy and paste some stuff from the notebook that's on GitHub, so we can do this quickly. But what I'm going to do here is I'm going to make a plot of, instead of the wine scores, I'm going to plot the prices. Okay, and the prices, so here I'm filtering out the prices that aren't specified, so I'm only looking at prices greater than 0. And then I'm going to plot it. So I'm going to plot the price. I'm going to make two side-by-side histograms, and one of the histograms is going to use a log scale, and you'll see why when I make this. So let me make this figure. Okay, so this is the distribution of the prices in this wine data set. So there must be some wines in this data set that are like $3,000 a bottle, and but most of the wines are pretty cheap, you know, down here in the less than $20 to $30 range. See this huge bar. This is just showing the same data, but now it's using a log scale on the vertical axis here, and that stretches out the data a little bit, so you can see there are a few examples of really expensive wines. There's one wine that's over $3,000, two, looks like two that are around $2,500, three that are around $2,000 a bottle. Needless to say, I will never be tasting any of those wines. They're probably not that much better. But this is an example of a data set. You know, if you look at this, right away, I mean, your eyeballs tell you that this is not normally distributed data. This data is not a bell-shaped curve. This data is more exponential. Most of the data is clustered around 0, and then you got this long tail where there's some really expensive wines. Also, there's no such thing as a negative price. I don't think they pay people to take wine very frequently. So the last thing I want to show you is, and you know, I'm just gonna keep going until I get through this. But if you guys have to leave at 10 o'clock, that's fine. But I want to get through this. You can come back and see it later. I want to talk about something called the central limit theorem, and what this theorem represents is that, well, let me take a step back. A lot of the stats that we'll do this semester are based on the assumption of normality, but that assumption isn't that the data itself is normally distributed, because what we'll find is a lot of the statistics are statistics that operate not on the data itself, but on the means of data sets. Or to say this a little bit more carefully, the stats deal with the means of repeated samples. So it's like if I went to this data set, you know, let's say that this data set represents the entire population of wines that have been reviewed by Wine Enthusiast magazine. So we have every single example. That's not the way you typically deal in science. You go out and you sample. It's like if you were studying, you know, trees in George Washington National Forest, you wouldn't go out and visit every single tree. You go out and sample some trees, and you try to infer something about the population from that subset. And so you could do the same thing in this data set. Instead of we can assume that all the wine data in the world is at our fingertips, but we can sample it. I can go and I can pull 10 wines and say, what's the mean of these price of these 10 wines? And then I could do it again, and I grab a different sample of 10 wines. What's the mean price of these 10 wines? Do it again, do it again. And so what you can do then is you can build up not a distribution, a histogram of the actual data, but a histogram of the sample means. Every time you sample, you calculate a mean and you plot it on your histogram, and you do it again and again and again and again. So you build up a distribution, a histogram of sample means. Okay. So here is the importance of the central limit theorem. What it says is that it doesn't matter what your underlying data looks like, what its distribution looks like. You're guaranteed that if you plot not the data itself, but the distribution of sample means, that distribution of sample means will approach a bell-shaped curve, a normal distribution, if your sample size is sufficiently large. So in other words, if instead of sampling 10 wines, I sample 100 wines, and I do that over and over and over again, my distribution of sample means is going to look better and better and better, more normally distributed. So the consequence of this is, you know, when we're learning about parametric and non-parametric tests this semester, many of those tests are talking about not is the data itself normally distributed, but is the distribution of sample means normally distributed. And the central limit theorem says that will be the case if your sample size is sufficiently large. In other words, if your data set is sufficiently large, you don't have to worry about whether or not it's normally distributed or not to use parametric statistics. All right, I said a lot, and it's probably in many ways, but you know, you'll see this again. So let me finish by showing you This, let me just go right to GitHub. All right, so here is the finished notebook for today's lesson. Let me just go down to the bottom here. And you see there's lots of text notes here as well. Forgive the spelling errors. But what I'm doing in this last cell here is I'm calculating, so what you're seeing here are the distribution of sample means for repeated samples from this wine data set. So here the sample size is 10, and the sample mean, the average price of those samples, is definitely not normally distributed. But if I increase the sample size to 100, it looks more normally distributed. The mean is higher, of course, because now you're, well, no, it's not higher. The because we're talking about the average, not the sum. And then this is what it looks like if you have a sample size of 1,000. So as the sample size increases, the distribution of those sample means becomes more normally distributed, even if the underlying data is not. All right. So that's it for today. I'm going to clean this live stream up and post it up to YouTube as a separate video. But there's a playlist on my channel which will collect all the videos for this class. Okay, and I will link to it on the Sakai site. All right, so you guys have a great weekend, and let me just remind you, if you get the email about registering for 461, you got to do that by the end of the day. Okay, you got to do that today, and you should be all set up, ready to go. Just got to go to Rail and put that in. All right, have a great weekend. I'll see you next week.